know well I'm a chicken fried. And cold beer on a Friday night, a pair of jeans that fit just right, and the radio.
Okay. So we just talked about, before we had the Laplace transform of that RLC network, and we had a polynomial that we wanted to find the inverse Laplace transform of. Now, if you look at the definition of the Laplace transform, it's on page 18. I'm trying to keep my hand out of the way here. Equation 210. And this says, if I want to find the inverse Laplace transform of something, of f of s, doing it via calculus, it's 1 over j 2 pi integral of s of s e to the st, you integrate it over ds, and you let s go from c minus j infinity to c plus j infinity, where c is a real constant such that the limits extend past all the poles of f of s. Now, in reality, though we find the forward going Fourier transform sometime I do it in a calculus, I've never had to find the inverse. When I say Fourier transform, y'all be patient, Laplace transforms. I never have to do the inverse Laplace transform by using this method. Instead, I always do it by this technique called partial fraction expansion. And we're going to talk about 3 different cases of partial fraction expansion. The first one is simple, non-repeated, real roots. And by this I mean if you've got a polynomial, we can say, like, if I said something like 5 over s plus 1, s plus 2. Here we see that the roots are -1. The roots of, if I multiplied this out, the roots of that polynomial would be -1 and -2. S equals -1, -2. Those are the poles of the whole thing, or the roots of this bottom polynomial. So in this case, they're non-repeated, and they're real. The second case we're going to look at is repeated real roots. So this might be a case where I've got 5 over s plus 1 quantity squared s plus 2. And the third case is where I'll have complex roots. And so this might be a case where I have 5 over s plus 1 plus j and s plus 1 minus j. Now, one thing, as an aside, one thing to remember, whenever you have imaginary roots, they always show up as complex conjugate pairs. The real part is the same, but the imaginary part has opposite signs. And the reason is because when you multiply them out, you don't have any imaginary pieces. So in the real world, there is no such thing. Real components don't have imaginary don't have complex components. Complex math is kind of a creation to make the math easier to work through. So whenever you see complex items, they will always show up as complex conjugate pairs. So if you ever, like here, I was going to draw the roots of this, the poles of this. I've got it at -1. There's a pole here and a pole here. That's -1, and that's positive j. That's negative j. So that root is at s equals -1 plus j, and that root is at s equals -1 minus j. So you'll always see poles and zeros when they're not on the real axis. They'll always show up, whether it's pole or zero, in a complex conjugate pair. Okay? Alright, so the next lecture, the next little video, I'm going to cover this case right here where we got simple non-repeated roots. Unfortunately, I got to keep these videos short because I think YouTube has a fairly strict limit on how big these videos can be. So I know it makes it kind of painful. Alright? So that's it for lecture 2.